please. Hi everyone, welcome to the third of what is now going to be a 5-part webinar series on decision support modelling, principles and practice. My name is Keith Brown and I am the Principal Hydrogeologist for Rio Tinto's Pilbara iron ore operations. So gauging by the attendance and the feedback we've for the webinars we've had so far, they have been well received, and from a GMDSI perspective, it's incredibly encouraging. Before we cross back to Kath and John to talk about it, I just want to plug the Q&A webinar. I think we need to have some more discussion on what actually is what makes a model adequate, and I'll just and from an internal Rio perspective is actually a lot easier, as I'll explain in a second. But externally, there's 3 parties essentially involved with identifying or working out what the adequacy of a model is. The person who is commissioning the model, they want to know that the work that they're getting that the model that is being produced is adequate or fit for purpose. The person creating the model, they want to know that that they are doing a good job, and then the person that's reviewing the model. These are not easy things to define or to describe. Internally, as I said previously, within Rio Tinto, it's much easier because we're an engineering company, and our language is based on risk. So, and that risk can be either an opportunity or a threat, but basically everything breaks down. All of those risks are broken down into likelihood and consequence. So for us, at the end of the day, risk is the uncertainty that matters, and we use those models to assess that risk. And as an example of that, John talked a little bit last week about the possibility or the potential of using analytical models. And we've been using those models, or analytical superposition models, for more than 6 years now. And they support our mine dewatering operations. And I think we currently use 20, possibly 30 of those models. So we've certainly moved on from that debate. And we also use those in some cases to support our environmental approval. But this is just an example, or a practical one, of how we use models as business support information tools. But it's more than that. It's a philosophy or a principle. But enough from me. I think I've already said too much, and I will be back with you when the Q&A session is on. So keep the questions coming in, and cross over to you, Kath.
So in the last 2 sessions, we talked about the implications of the abstractions and simplifications that we need to make in groundwater modelling for decision support. Keeping all that in mind, in this and the next session, we start to talk about some of the specifics of data assimilation and uncertainty analysis. Today's session will cover these 4 main topics. But first, a bit of revision of the last 2 sessions. We started by saying Bayes' equation is our guiding light. It defines our task in model-based decision making so that we can assess the risk of an unwanted event occurring. Mathematically, Bayes' equation shows us that we must blend information from 2 very different sources in our model. Our first source of information is site characterization data and expert knowledge, which is represented stochastically because of the lack of subsurface information. This source of information defines our prior probability distribution. Our second source of information are historical observations of the system, which allow us to condition this prior. However, Bayes' equation does not show us how to design and undertake decision support modelling to achieve this blending process. Happily, Linear analysis does provide insights into how to blend this information. We can identify those parameter combinations that are informed by historical observations of system behaviour which reside in the solution space. We can also identify null space parameter combinations. These are uninformed by historical observations and instead must be informed by site characterisation and expert knowledge. Tracking the flow of information through this kind of analysis makes it clear that the prediction and the data that is available should be the basis of the model design. This fundamental decomposition of parameter space allows us to define 3 categories of prediction for which different model design approaches are required to enable the flow of the information that matters to the predictions. History-based predictions are generally similar in nature and location to the measurements used in history matching. Attainment of a good match between model outputs and these measurements generally ensures that these types of predictions are unbiased and have little uncertainty. Expert knowledge-based predictions occur where historical observations contain little information that can reduce these uncertainties. Modelling to make these type of predictions can then adopt complex geostatistical methods or simply worst-case scenario analyses. The blended information prediction category is both the most common and the most challenging for decision support groundwater modelling. This category requires that a model be highly parameterised to assimilate decision-relevant data while ensuring that the integrity of both the solution and null spaces are maintained. This is required firstly to avoid bias in our estimated parameters and the predictions that depend on them, and also to ensure that predictive uncertainty is not underestimated. And it's this category that we focus on today and in the next webinar. We also discussed how our industry sits at the intersection of a number of specialties from which we borrow knowledge and inspiration. In groundwater modelling, there are compromises in implementing all of the methods derived from these other specialties. So decision support modelling in groundwater is a specialty of its own, and it has its own unifying principles. And these are listed here. We have Bayes' equation that defines what we need to do to provide decision support. We have a metric for decision support failure, ensuring uncertainty quantification errs on the side of caution. And we have a roadmap following the flow of information that provides the basis for decision support workflows. And now we'll talk about the tools. So I'll hand back to John here.
Hello, everyone. Firstly, if my words sound a little bit slurred, it's because I'm again having some difficulty with the internet connection. If it's too bad, someone will tell me and we'll go to plan B. Okay, I want to start talking about what I like to call model dancing partners. Now, we said in webinar 1 that the decision support modelling is so much more than just simulating what happens under the earth. We're not very good at that anyway. Simulation is meant to serve data assimilation, the implementation of Bayes' equation. And just to further accent that, I want to say a few words about the software that we have to use with our simulator, the model. As again, I like to call them dancing partners, and these are as indispensable to the decision support process as the simulator. If decision support groundwater modelling is all about data assimilation, for reasons that we'll talk about, that means that we've got to run the model lots and lots of times, and it's got to be run in smart ways. And that's why we need partner software, such as members of the PEST and PEST++ suite, which are every bit as important as the simulator itself in allowing us to achieve our aims. And what is our aim? Implementation of Bayes' equation. So let's just spend a few moments focusing on what is the model that we're often using in the data assimilation framework. So we might have a simulator. Well, we've got to have a simulator, that's why we're here. We might have 2 simulators. We might, for example, be simulating flow and transport. or we may be simulating flow and then perhaps electromagnetic response with another model, which is linked to the groundwater model, so that we can then use electromagnetic data in the data assimilation process. The groundwater model may require one or a number of recharge models, which provide recharge to different land uses and soil types within the model domain. There'll be a necessity to have a parameterization scheme, something we'll talk more about shortly. So there's got to be something, some utility programming running in front of the model that distribute numbers that comprise parameters to the various model instances that comprise the simulator. At the back end of the model, we've got to have something, some other piece of software, a utility program, that can undertake spatial and temporal interpolation from the outputs of the model to the sites and times at which we have field measurements. And then, as we talked about last week, we may have to then do further processing of those model outputs to match the field data processed in the same way so that we can bypass the deleterious effects of model defects on some of our estimated parameters to avoid bias in estimation of those parameters. So our model is so much more than just the simulator if we're going to be working in the decision support process. The model is actually a chain of processing. Altogether, this is with utility programs wrapped around the model, which then allow it to wander and work in this decision support framework. So, all these programs together, some simulators, pre and post processors, they're going to be all encapsulated in a batch or script file, depending on what system we're using. And at the beginning of this whole processing sequence, there's going to be sets of input files, and sets of output files are going to be at the back of this whole processing sequence. These, on our computer, these comprise the data assimilation boundaries. These are the places where parameters come into this chain of processing and where outputs corresponding to field observations come out of this chain of processing. These are the places to which the dancing partner software must link when it runs this model, which, as we can see, can be a fairly complicated thing, to do what decision support modeling requires: assimilation of data, quantification of uncertainty. So here we've got the simulation, we've got the model, which can be quite complicated. We've got input files and output files. And as I've just said, we need the dancing partners which can work with the model to allow it to do what decision support modeling demands: assimilation of information, quantification of uncertainty. And I just want to mention two fundamental specifications of the software with which a model must dance if it's going to implement this decision support imperative. The software, which is just as important as the simulator in taking us to the places we need to go if we're going to do decision support modeling properly. So, the first important specification of such software is that it has what we call a non-intrusive interface with the model. The model can be complicated, and we may have exercised a lot of creativity in how we design this model, in the way we parameterize the model, in the way we define an objective function that is minimized through the history matching process. Any good idea we have, or not so good idea we have, can be put in here as another processor, another utility programming in this processing sequence. The non-intrusive interface means that this dancing partner can interact with the model, no matter how complicated it is, through the model's input and output files. We don't have to have the model source code. We don't have to be a programmer. The model can be whatever it needs to be to encapsulate that chain of processing that's required for this particular decision support implementation. So that's our specification number one, that this dancing partner, which will need to run this model hundreds, maybe thousands of times, can interact with this model through the input files and output files, one or many, that are read and written by this model, which can be arbitrarily complex according to the creativity we apply to the decision support context that we're working in. The other fundamental design specification is that these model runs be parallelizable. Now, as we'll talk about shortly, this is going to take a lot of model runs, especially if we're working in highly parameterized contexts, which we must if we're working in this blended information context, which Catherine just mentioned is the focus of our attention in these last two webinars, highly parameterized history matching. So here we've got a numerical engine. This could be inversion. This could be ensemble filter. It could be one of the dancing partner functions that is essential to decision support modeling. It's connected to a run manager. That run manager is connected to the world through TCP/IP, the messaging, the communication device used by the internet. And over here and other places, perhaps in different folders on our same machine, perhaps in folders on other machines in an office network, perhaps running in folders on the cloud, we have things called agents. And agents do the non-intrusive interface with the model. So the numerical engine says to the run manager, I want these parameters to be used for this model run. The run manager finds an available agent, sends it the parameters over TCP/IP, tells the agent to run the model. It doesn't even know where the agent is. The agent runs the model, sends the outputs back, the engine processes it, and so it goes on and on and on. And many of the things that we have to do when using the modeling in the decision support context allow these runs to be conducted in parallel because they're independent of each other and hence ideally parallelizable. This then is the second important specification of the model dancing partner. Without the model dancing partner, how we can do decision support modeling properly. The days where we calibrate a model by hand using a limited number of parameters, for reasons I hope we've made very clear, should be over. If our task is to assimilate information, quantify uncertainty, we have to live in a highly parameterized world if we're dealing with predictions that are informed by two different data types pertaining to two different scales. Highly parameterized history matching is not an option, it's an essential. This requires many model runs. This requires a non-intrusive interface with a model by a dancing partner that can also parallelize those model runs. This is essential to modern day decision support modeling. And PEST and PEST++ have these specifications and can be the dancing partners. So now I'm going to say a few words about model calibration. Now, Catherine talked about model calibration a little bit in the first webinar, so there's a little bit of revision here, but there's also a bit of new stuff. Now, I think calibration is one of those terms that needs a little bit better definition. We often tend to use calibration as a substitute for history matching. But I think we've got to be clear about this. History matching is history matching and calibration is also history matching, but it's a special type of history matching. Calibration implies uniqueness. Now, I've already said, when it comes to history matching in the context of groundwater modeling, if we think there's uniqueness, we're dreaming. There is no uniqueness. There's 100, 1,000, a zillion ways to fit history. Ideally, when we're looking at the uncertainty of decision-critical predictions, we may have to actually replicate the historical behaviour of the system hundreds, thousands of times and come up with many different parameter fields, all of which allow the model to replicate the historical behaviour of the system, all of which are then used to make a prediction. That's what we talk about in the next webinar. Calibration, though, has a sense of finality about it. It implies uniqueness. So why calibrate if calibration implies uniqueness, where we've already said that uniqueness has no right to exist? Well, there are some benefits in this. It's not essential, but I think we have to realize what calibration is and what it isn't. Calibration is the pursuit of uniqueness, where uniqueness has no right to exist. And I hope we all know now that calibrated models should not be the end point of decision support modeling. It's halfway to what we require is quantification of the uncertainties of predictions. Uniqueness and quantification of uncertainty do not go together. Nevertheless, calibration, uniqueness can have a purpose if we're very careful about what we're trying to achieve through calibration. Uniqueness, where uniqueness has no right to exist unless we define conditions which actually give us uniqueness, and unless those conditions are good for our purposes working in the decision support context. And it just so happens we can do that. So he said last time that information that is relevant, that is resident in measurements of the historical behaviour of a system, the information flows to a space, a subspace of parameter space, that is actually defined by this information. This subspace is comprised of combinations of parameters which can actually be uniquely estimated. Not without uncertainty. There's noise in this data. There'll be uncertainty in these unique estimates of combinations of parameters that comprise the solution space. But then there's the large and vacuous null space. The only way that can be informed is, well, we've been saying up till now, probabilistically, based on the stochastic nature of expert knowledge. But if instead we say, no, let's just give all these combinations of parameters a unique value, a common sense value, a value that makes sense to us as experts, a value that lies at the center of the prior probability distribution of these combinations of parameters. Combine the two and we have uniqueness. And we have uniqueness in a very special way. We have uniqueness that if we do everything properly, allows us to make predictions of minimum error variance. Minimum error variance because they are wrong and hence they're in error. But the wrongness, the potential for wrongness is symmetrical about the predictions we make. That's why it's minimized, because it's like having we stay in the middle rather than betting on this side or this side. So mathematically, it can be shown that we can attain uniqueness, and we can attain uniqueness in a way that makes sense, that it does have utility in the decision support context. Okay, so when we do this then, if we follow all the rules, and we'll talk a little bit more about the methodology in a moment, we attain an average parameter field. We attain a parameter field that is unique in its ability to provide predictions made by the model that are of minimized error variance. We have a platform for post-history matching, post-calibration uncertainty analysis. But for me, most importantly, we have an ability to test the hypotheses on which our conceptual model is based. We all know that calibration doesn't happen just once. We history match, we find that we don't fit history very well. We've got to adjust our model. Or that we only get a good fit with the historical behaviour of the system if our parameters are stupid? Well, we learned something. They're taking on surrogate roles, compensatory roles, for some defect in the model. And there's a lot to be said for engaging in this pursuit of, is my model, as my numerical model, as it rests on my conceptual model, does it have the correct receptacles for the information content of the calibration data set on the one hand, expert knowledge on the other? If we seek a good fit with the historical behaviour of the system in a way that says, please, PEST, if you're using PEST, deviate from what I think are common sense properties only to the minimum amount required to fit the data, and fit it well if we think it's worth fitting well. That way, if we can't fit the data well, or if what it takes to fit the data well is stupidity of parameter fields, we immediately know we got to do a little bit more thinking. Our conceptual model may need revision, and we can make the necessary adjustments. And working with minimal departures from common sense, common sense from a prior position, from an expert knowledge point of view, allows us fairly quickly to test the hypotheses on which our numerical model is built. But it's not the final step. As we keep saying, the calibrated model should not be the deliverable in decision support modeling. What we need to do is quantify the uncertainties of decision critical predictions, and uniqueness does not allow us to quantify uncertainty. So how do we go about this? So suppose we've got a model domain here, and we say, well, let's use lots of parameters because our context in this webinar is highly parameterized inversion, because we're mixing data of very different types pertaining to very different scales. The parameter combinations that we can't estimate are just as important as those we can, because that's the source of a lot of predictive uncertainty. At the same time, we want to provide maximum flexibility in here for information that resides in this history matched data set to go where it needs to let heterogeneity arise where it needs to, in ways it needs to, so that we have receptacles in our parameterization scheme for whatever information appears that is resident in this history matching data set. So we may use pilot points. We don't have to. There are other parameterization devices, but for reasons we'll talk about in a moment, this gives us the ability to work with lots of parameters. So then we use a thing called Tikhonov regularization. This actually comes from the geophysical industry. There's many ways to implement it. One way is this. We do like what I was saying before. We say, let's give each one of these parameters a value that makes sense from a prior point of view. They then become the encapsulation of our expert knowledge. And then we tell PEST, all right, now adjust these parameters. You've got more parameters than you can poke a stick at. You should be able to get a pretty good fit with the data. Adjust them, so you do. But we tell PEST, do not overfit. There's a button in there we can press, and we can say, just because you've got a lot of parameters doesn't mean you have to overfit. Do not let the goodness of fit exceed this amount. So we can stop that. We can put overfitting to bed very easily. And then part of our Tikhonov constraints, as they're called, is that we say, to the extent that heterogeneity should arise to allow us to fit the data, let it arise only to the minimum extent required to achieve that fit. And, oh, by the way, let it arise in ways that make geologic sense. And all this geologic sense can be put into matrices that we can use, numerical devices that we can use to make sure that heterogeneity arises only as much as is necessary and only in ways that make sense. So, this is behind the scenes. There'll be an equation like this. Here's our field data. Here are our estimated parameters. These are all matrices. If you want to do anything on a computer, you got to be using matrices. This encompasses our ticking off regularization. This can be complicated as you like and can be very clever in the way it gives mathematical expression to the way heterogeneity should arise in geologically meaningful ways. And this matrix, which you're going to hear a bit more about in the next little while, is the justly famous J for justly, J for Jacobian matrix. The first column of the Jacobian matrix is the sensitivity of all outputs of that long chain of processing, which is the model, all outputs to which we match field observations. It's the partial derivative of all of those with respect to the first parameter. Partial derivative with respect to the second, third, fourth, and if we've got 10,000 parameters, this will have 10,000 columns. And if we've got 100,000 observations, this will have 100,000 rows. At the crux of any history matching in the highly parameterized world is a Jacobian matrix or something that approximates it. This is an iterative process. It means we've got to use this equation again and again. We take our data, get a better set of parameters. That doesn't give us a good fit yet. Calculate another Jacobian matrix, repeat this implementation of this equation until the process converges, and hopefully we get a good but not excessive fit with our field data. All right then, the Jacobian matrix lies at the heart of all this. How do we calculate this? Well, if we're, for example, using geophysical models, the models they use can calculate the Jacobian matrix themselves. There are ways that using groundwater models this can be done too. However, it's fairly complicated. Then when we want to be very creative in what we call the model, for the reasons we talked about a few minutes ago, then we can't really do that if we've got to follow anything we do with the programming necessary to calculate the Jacobian matrix. So normally, even though it's incredibly efficient if that model can calculate its own Jacobian matrix, it's not something we can do in groundwater modeling. We can calculate it using finite parameter differences. So we can undertake a model run in which we incrementally vary parameter P1, look at the change in model outputs that result, divide the change in model outputs by the change in parameters, and that's an approximation to the partial derivative. Repeat for column 2, column 3, etc. Obviously, lots of model runs. If we've got 10,000 parameters, this requires 10,000 model runs. And lately, bursting onto the scene are randomized and ensemble methods. We can get efficient approximations to this Jacobian matrix using these methods, maybe with only a few hundred model runs per iteration. We can often get a really good fit with the data very cheaply using these methods. However, the Jacobian matrix, or the approximation to the Jacobian matrix thus calculated, doesn't really then form a good basis for linear analysis, which we'll talk about shortly. This, of course, requires the dancing partners. These, the indispensable partners to the model when it comes to decision support modeling. Before we move on to linear analysis, just a couple of words about pilot points as a parameterization device. I was asked about this at the end of webinar 1. If we're using pilot points, the way this operates is that PEST assigns values to these points, and then giving hydraulic properties to the model becomes a two-step process. PEST gives values to pilot points. A little pre-processor here running in front of the simulator in this chain of processing does spatial interpolation from the pilot points to the model grid. The good things about pilot points, well, we can live in a highly parameterized world. And we can use finite differences to calculate a Jacobian matrix. The bad thing, well, pilot points aren't exactly reality. The world isn't made of points. You don't see pilot points as you drive across a field site. They are an artificiality. How many should you use? As many as you can. Placement can be subjective, but the more you use, the better. The big mistake is to use too few. There's only one thing worse than zones of piecewise constancy in a model, and that is circles, and that's what you'll get if you use too few. So use as many as you can, then you'll be right. Just one example. This was done by a colleague of mine who used three-dimensional pilot points near a pit. He was building a model to look at inflow to a pit. Two-dimensional pilot points to look at regional heterogeneity, and a set of one pilot points along various faults that intersected the pit. And these are maps of the coloured according to the log of inferred hydraulic conductivity. Okay, now let's move on to linear analysis. And very soon I'm going to hand back to Catherine, but I'll just present the concepts and then she will present plenty of examples. So here we are with our model, as happy as can be. Here's the past, and we've just done history matching. And there is the future. And we want to make predictions. So, and the model is linking the past with the future through the data assimilation imperative, which it is carrying out. So just say we've calculated a Jacobian matrix, as we will have done if we've calibrated the model. Now, we don't have to calibrate a model to do linear analysis. All we need is a Jacobian matrix. This can actually be done using initial parameter values, just values that make sense for us. We don't have to have history matched, but often we do this after we've history matched. So we've got a Jacobian matrix here, the sensitivity of model outputs used in the calibration process to parameters. Let me calculate a predictive Jacobian matrix, sensitivity of predictions to parameters. These matrices have to have integrity, so often they'll be computed using finite differences. Obviously, this can get expensive if we've got lots of parameters. So let's just flip things around. There's the past on the top, there's the future down the bottom. And we're replacing the model with a matrix. The model in the past, the model running into the future. That is, we are linearizing the model. When you replace something with a matrix, you are linearizing it. So we now have the model. We have a replacement for the model, a matrix. So this is approximate because models aren't linear. However, it's not a bad approximation in a lot of cases. Furthermore, the outcomes of linear analysis are still often really usable, even though they're approximate. We talk about non-approximate ways to do uncertainty analysis next webinar. So we just need two more matrices and we're good to go. We need a thing called the prior covariance matrix of parameters, and we need a thing called the covariance matrix of measurement noise. Now, I use that word noise very loosely. It's just whatever it is that causes model to measurement misfit. Let's call it noise because it's really that and model defects, but the statistics of model defects are a little bit too horrible to contemplate. We normally just call it noise. So let's just have a quick look at how we calculate these. This prior covariance matrix, if we've got 1,000 parameters, this has got 1,000 rows and 1,000 columns. If you've got 10,000, it's got 10,000 rows, 10,000 columns. It looks daunting to construct, but it's not. It's easy, really. The diagonal elements are just the prior uncertainties of the parameters. Your jobs as modelers, as geologists, is to know the prior uncertainty of these parameters. That's why we do site characterization. You know the geology, you've read the textbooks, you've done the pumping tests, you know the prior uncertainties of the hydraulic properties. If not, you guess, and guessing is okay because they're uncertain. But there's upper and lower limits to the guess you'll make because they're uncertain, and even though we don't know exactly the properties, we do know their limits. And then these off-diagonal elements. Well, they just reflect the fact that properties are spatially correlated. Geology is continuous. The property at point A is not completely independent of the property at point B if B is close. So we can put off-diagonal elements to represent prior spatial correlation. It sounds hard, it's easy. There's plenty of utilities available in the PES suite and the PyEmu suite that'll automate the construction of this matrix for you, just requiring your expert knowledge and perhaps definition of a variogram. Now this matrix, this is even easier. If you've calibrated, you know the sort of fit that you've got with the data. If you haven't, you can guess it. The diagonal elements of this matrix just reflect the fit, the misfit that you get at each of the data points that were used in the history matching process. That matrix too is easily computed using utility software. Once we have those matrices, the world is our oyster. So here we are back at Bayes' equation, the place we started 2.5 webinars ago. The light that guides us in decision support modelling. The rules we must obey if we're going to do this properly. It says prior uncertainty, turn it into posterior uncertainty through data assimilation. Here's the prior covariance matrix, which we've built in ways we've just talked about. Here is the posterior covariance matrix, that is the post-history matching uncertainty and correlation of all our parameters, easily calculated using this equation. This equation is full of matrices, easily implemented on a computer. There's our CK, there's our C epsilon matrix, there's our Jacobian matrix. This is Bayes' equation for a model which is linear. We've got our posterior parameter uncertainty in one equation, and sensitivities are at the heart. And we can go a little bit further. Just by adding these predictive sensitivities to this equation, we can calculate, just through a matrix equation, the prior uncertainty, the prior variance, the prior standard deviation of any prediction, and the posterior standard deviation of any prediction. We have implemented Bayes' equation in one easy step. That's the theory, and now I'm going to hand over to Catherine for lots of examples.
So the linearized Bayes equation, while approximate, is very powerful. We can assess the uncertainty of any parameter combination or prediction very quickly. And we can assess this both before and after history matching, because we don't need to know the magnitude of a parameter or a prediction to be able to assess its uncertainty. All we need are those 4 matrices, the sensitivity of the parameters to model outputs corresponding to the data that we have, and the sensitivity of the prediction to those parameters, and then the covariance matrices of our prior parameters and our measurement noise. And we can also decompose this uncertainty to look under the hood of our parameter prediction relationships and see the contributions that individual parameters and groups of parameters make to our prediction uncertainties. And we can also decompose this uncertainty to look under the hood of our data prediction relationships. We can quickly assess the worth of existing and imaginary data of all types in terms of how much that data can reduce the uncertainty of the prediction. And the worth of data rises in proportion to the extent that it reduces the uncertainty. This is possible because we can calculate the prediction uncertainty as a function of our pre-calibration uncertainty less the conditioning effect of measurements. And so because this equation features neither the value of the parameters or of the observations, just the sensitivity of the parameters to those observations and the sensitivity of the prediction to the parameters, we can look at the worth of data even before it's gathered. Let's see some examples of parameter statistics using linear analysis. So we just saw that the equations that we use have a historical and a future sensitivity matrix, but for a moment, we'll just look at some examples that focus only on the parameters. So we'll just use the historical sensitivities as provided in the Jacobian. So armed with the Jacobian and linear parameter uncertainty analysis, we can analyze parameter space to define the parameter combinations that reside in the solution space and the null space. This allows us to track the flow of information, where it comes from and where it goes. It also provides the dimensions of the solution space so that we can know how many unique usable parameter combinations that can be estimated on the basis of our historical observations. In our experience, there's typically less than 200 unique parameter combinations, even when we have thousands of observations and thousands of parameters. And we can even find out exactly what those specific parameter combinations are if we want and plot them. But we know more than this. We know that any single parameter can reside partly in the solution space and partly in the null space. And we can define a number called identifiability, which describes the extent to which the parameter resides in either space or somewhere in between. So our identifiability varies between 0 and 1. And the identifiability of 1 means that the parameter resides completely in the solution space and so is uniquely estimable. It may still be uncertain, but history matching will give it a unique value, and any uncertainty that will occur will be from model to measurement misfit rather than a lack of knowledge. If, on the other hand, identifiability has a value of 0, then the parameter resides entirely in the null space. And for those parameters somewhere in between 0 and 1, information from historical observations is shared between this parameter and other parameters. It can't be resolved uniquely. So identifiability can be plotted like this on the figure on our left, where we have a model with 54 parameters, and we can immediately see the status of each parameter. Some parameters at the top of the system are uniquely identifiable, and for other parameters, the data has nothing to say, and many parameters are somewhere in between. So again, what does in between mean? It means these parameters are not uniquely estimable, and instead the information is shared between this parameter and other parameters. This graph is easy to produce. We only need the Jacobian matrix and our parameter and measurement noise covariance matrices. And straight away, we know the identifiable status of each and every parameter. We can also quickly assess how additional data can improve identifiability. Here, a model on the right was used to explore the return on investment in geophysics data. In this case, electromagnetic data is added to head data and significantly improved the identifiability of the 350 pilot points that are shown in this plot. We can also show identifiability spatially by mapping it. And this is for a model in Florida that John was involved in. And it's clear to see that identifiability is related to the data density. Identifiability patterns also allow different parameter data relationships to be seen. That is, how well are different parameters informed by the current available data. For example, in this case study from a recent MSc student, hydraulic conductivity on the left is best informed by our current data set, even by sporadic water level measurements, which are shown by those black dots. In contrast, storage and recharge parameters tended to be better informed by regular daily water level measurements, shown by the pink dots. A slightly better statistic with a slightly different emphasis directly uses the linear expression of Bayes' equation to assess the relative reduction in uncertainty of each parameter that's achieved through history matching. While identifiability conveys the transfer of information or not to individual parameters, the relative parameter uncertainty reduction incorporates the mixing of historical and expert information as described in Bayes' equation. Once again, this description varies between 0 and 1, and the closer we are to 1, the more uncertainty has been reduced through history matching. We tend to prefer this description over identifiability, because identifiability can be sensitive to the dimensionality of solution space, and sometimes the parameter space subdivision can be a little grey, and so mid-range identifiability values themselves can be a little uncertain. So here is the same model area again, but this time showing the relative parameter uncertainty reduction varying between 0 and 1. We see a very similar pattern to the identifiability plot. However, note that this pattern is slightly more spread out. This is because the expert knowledge in the prior parameter covariance matrix is now represented. This matrix describes the spatial correlation structure of hydraulic conductivity, which reflects the connectedness of the prevailing geology. And once again, this description reflects where we have data. And significantly, where there is little data, a well-calibrated model may have no more predictive power than a model that is not calibrated at all. And we can see this in some parts of this model domain with the light blue shading. So now we're going to bring back our predictive sensitivity matrix and track the flow of information from data to parameters to our prediction. And we'll show some other examples that look under the hood of our data prediction relationships and get a glimpse of the wealth of insights and benefits from being able to do this. So now, because we're looking at the future, we add our prediction sensitivity matrix on the right back onto Bayes' equation. Our first example is an everyday model built by colleagues, and it's used to provide forecasts of mine pit dewatering rates over time. And here we see the hydraulic conductivity after history matching through the model domain in the third model layer. Using linear analysis, maps were produced which show the uncertainty in head forecasts in every model cell as the mine pit deepens over time. And again, using linear analysis, the uncertainties of pit inflow forecasts were quantified. Another example shows a model of an irrigation area. This was a model done by other colleagues, and here we can see the hydraulic conductivity distribution again after history matching. And using the model was then used to make predictions of the water table at the end of a dry period. And using linear analysis, they calculated the uncertainty of every predicted head in every model cell. And now just focus on this rectangle in the middle of the model domain, where we have an average head over a number of model cells at the end of the dry period. Using a variation of the same formula, we can examine which parameters or parameter groups contribute most to the uncertainty of our prediction, in this case, the average head in our rectangle. We can see how this differs pre and post history matching, where the back row in this plot is for pre-history matching and the front row for post-history matching. So at a glance, we're able to see if history matching has reduced the uncertainty of the prediction and how it's done this. We can also introduce parameters to our model that would not necessarily be incorporated into history matching to see how they affect the prediction. For example, we can explore the impact of boundary condition specifications on the uncertainty of our prediction. In fact, we can use this equation throughout the model design process to inquire into the effect of simplification strategies on the ability of a model to make a particular prediction. These simplifications may be, for example, omitted or lumped recharge processes or simplified boundary conditions. For example, focusing on simplified boundary conditions for our average head prediction, we can inquire, are these boundaries too close? And in this case, no. Why? Because the contributions of the uncertainty in their specifications to the uncertainty of our prediction, our rectangle average head, is calculated to be low. Or similarly, what about the coastal head boundaries or the river stage? If they are somewhat uncertain, how does this affect the uncertainty of our prediction? All we need to do is assign a prior probability distribution to these potential errors in these boundaries and plug this into our equation and calculate the contribution that that potential boundary inflow uncertainty makes to the uncertainty of the prediction. Another variation of the same formula allows us to examine which part of the history matching data set is most effective in reducing the uncertainty of our prediction. And in this case, for our rectangular average head prediction, transient head data is the most informative. We call this a data worth assessment, and we can do this in two ways. We can work out how much each set of observations would reduce the uncertainty of that prediction, starting from a position of having no data. Alternatively, we can evaluate how much we would miss each set of observations if the data wasn't gathered in terms of an increase in the uncertainty. This therefore informs us of the unique information content of these observations with respect to our predictions. We can also show data worth spatially. This model was used to simulate the increase in duration of low flow periods at 2 points in a catchment under a proposed groundwater pumping scenario. The photo shows the river at the bottom of this catchment, which is in Gore in the bottom of the South Island in New Zealand. And bigger black dots show the best place to position additional monitoring wells to inform these predictions. We see that a lower mid-catchment prediction was best informed by wells immediately up gradient of that stream location. In contrast, the prediction at the bottom of the catchment at Gore was best informed by wells in the uppermost part of the catchment in our left-hand side plot. And initially we were surprised by this result. However, it makes sense if we consider that this is a fast-moving system and the wells at the top of the catchment have large water level fluctuations compared to the bottom of the catchment, and hence a much larger information content. So this analysis can sometimes make obvious what's not initially intuitive. A final data worth example involves the design of a tracer test. The tracer test was being used to inform predictions of the dilution and travel time of a hypothetical contaminant associated with the reinjection of treated coal seam gas water. We investigated how many wells should be monitored, how frequently, where they should be located, and what they should be monitored for. And the conclusions came with significant cost implications. For example, we examined how many wells are needed to get the most prediction relevant information out of the tracer test data. And in this case, 2 wells were more than sufficient. And afterwards, there were clear diminishing returns in any additional reduction in uncertainty if we had more wells. We also explored what were the most cost-effective analytes and monitoring frequencies of those analytes during the tracer test to best inform our predictions. The tension between the cost of an analyte and its effectiveness in reducing the uncertainty of the prediction can be plotted against each other. For example, we have analyte 1, and we can see that analyte 1 can reduce the uncertainty of the prediction with increasing sampling costs, for example, because of increasing the frequency of sampling. But analyte 2 is better, as for the same cost, we get a reduced uncertainty. So this cost-effective analysis was also used in our tracer test study to indicate the best sampling frequencies of bromide, chloride, and methane. So at this point, I'll hand back to John.
So just to wind up, 2 things. Firstly, there are other types of linear analyses we can do, and we've been using the word linear analysis rather than sensitivity analysis here, and in some ways it's a matter of semantics, but I do think there's a lot of confusion around what is sensitivity analysis. A lot of people ask for sensitivity analysis, and I often wonder what they're really, if they know what they're really asking. At the centre of all the analyses that have just been done is a Jacobian matrix. It is based on sensitivities. However, with the addition of those other 2 matrices, we get so much more information. And in the end, when a lot of people are asking for sensitivity analysis, they're probably really asking for uncertainty analysis but didn't know to ask. Now, still, we often see things like composite scale sensitivities being used and asked for. We haven't talked about those because we tend not to, I tend not to use them much now. These were pretty well used in the old days where we had to have parsimonious parameterizations of a model when we wanted to calibrate. Well, for reasons we've talked about extensively, those days are over. We don't need composite scale sensitivities to tell us what parameters to take away. Anything, if it can wiggle, let it be part of the parameterization of the model. So for all the reasons we talked about, quantification of uncertainty and getting the null space solution space boundary correct so we don't incur bias in predictions. So I don't use these much at all now. There are other analyses that you can do with linear analysis. You can try to work out what is causing your misfit. Is it that you haven't provided enough receptacles for the information that you've got? Do you need to provide more receptacles? There's utilities available from the PES suite can help you point the direction to that. And also, is my model simplification inappropriate, and is history matching engendering bias in some predictions? Still other utilities can explore that issue. So there's no end to what we can do once we turn our model into a matrix, make it linear. All kind of information, all kinds of insights are available to us through various types of linear analysis, at the heart of which is a Jacobian matrix or two. Finally, global sensitivity analysis. Again, I think we're somewhat confused in what we call sensitivity analysis. That's why what we've talked about, we've called linear analysis. Everything we've talked about is based on a Jacobian matrix, which is kind of local. The elements of the Jacobian matrix, well, their values are going to depend on just what the parameters are. If a model were linear, it wouldn't, but models are not linear, so the values, the elements of that Jacobian matrix will be sensitive to the values of the parameters. Therefore, the information that we're getting from linear analysis, A, is approximate, and B, there are some things that perhaps we'd like to know, which analysis just based on a Jacobian matrix will never tell us. And those other things we'd like to know can be made available to us through global sensitivity analysis. Now, this is sensitivity analysis, which is a speciality unto itself. There's a lovely review of what this can be used for in this paper that you can see on your screens now. With global sensitivity analysis, parameters are varied over their full range. Normally, the number of parameters that can be involved in this kind of analysis is restricted. It can't be thousands or tens of thousands. But the idea is we don't just look at the effect that a parameter has on a particular model output. We look at how that effect varies with the value of that parameter, how it varies with the value of other parameters. Therefore, we get a sense of the importance of that parameter and, by inference, the processes to which it pertains, and how that parameter and, by inference, the process to which it pertains interacts with other processes. So it's much more comprehensive. The paper says that Pianossi et al. Say that there's three main uses to which global sensitivity analysis can be put, and they are listed here. Often in the literature I find it's applied to great big models which people have built to try to understand a system, not necessarily the models that you'd use in decision support for data assimilation. But by understanding the parameters, by understanding their sensitivities, by understanding the interaction of those sensitivities, one is in a much better position to then, if you want, build a more simplified model which incorporates the important aspects of the system which are exposed through global sensitivity analysis, and that simpler model may be the one that you then take into the data assimilation decision support process. If you want to do global sensitivity analysis, there's a member of the PES++ suite named PES PP GLM, which will do it. It requires a lot of model runs. The more model run parameters you have, the more model runs. Dancing partners, once again, essential for this activity. So in conclusion, what we just covered in the last hour, you can't have decision support modeling with a model on its own. It's a dance. The model has to be complex and it's got to be creative in its construction. It's got to have a sequence of processing steps, and it's got to be used in a dance with software such as PEST or PEST++ with a non-intrusive interface that can parallelize model runs to carry out the imperatives of decision support modeling. We looked at calibration. We said it's really got to be defined what calibration is. The word's used too loosely. It is not history matching. It's a special type of history matching that seeks uniqueness in a way that can serve the decision support imperative well if it's properly done. We've said that calibration, history matching of any kind requires a Jacobian matrix, and the uses to which we can put that Jacobian matrix in linear analysis to get approximations to parameter and predictive uncertainty, and to track that vital flow of information from the data, from expert knowledge, through the model, through the parameters, to the predictions. All of that stuff which we said in webinar 1 is essential to decision support modeling. We can do that and track it using linear analysis. And then we just briefly mentioned global sensitivity analysis. Not so much used in groundwater modeling, probably could be used a lot more than it is to great effect. That's the end of this webinar, and in the next and final webinar before we have our discussion webinar, we will look at nonlinear uncertainty analysis and touch on the topics shown.